Good morning, friends of the Golita Library. I want to thank you for giving me the opportunity to give this talk. My kids used to spend time at the library and borrow a lot of books from there, and I think every kid should have a library available. I spent a long time at the library in Iceland where I grew up, when I was growing up, and I think the Golita Library is a great institution that we should work hard to preserve. Now, today, I would like to tell you about the hidden structure of nature, which consists of fractals. You know, most of nature is actually constructed out of fractals, even though we don't quite realize this when we go outside and look around. And I would like to change your perspective of the world a little bit. So I'm going to tell you about the hidden structure of nature, which are fractals. And before I do that, let's take a look at some fractals to understand what they are. And the simplest fractals that we can think of are probably the Koch snowflake. Let me make sure that I have the Koch snowflake here. Yes. You may have heard that snowflakes are fractals. And there was a German mathematician, Helga von Koch, who tried early last century to try to make one, to understand, you know, the structure of a snowflake. So what she did was that she took a triangle like the one that you see here on the screen, an upside down equilateral triangle. And what she did was that she removed the middle third of all the sides and added a corner, you know, replaced the middle side with a corner where the sides of the corner had the same length as the part that she had just removed. And if you do that, in the first step, you're going to get a nice star. See, I removed this side and I added a corner of, you know, with the sides of equal length. And I did it for all three sides. You know, this is the original corner, which has the same shape as the other corners. But here I had to add an additional corner and on those two sides as well. And then we do it again. We take the straight side, we remove the middle third, 1/3 segment, and we add the corner of equal sides. And you can see that we're getting something which has more corners. And we can continue this. In theory, we could continue it forever. In practice, we won't continue it forever, but, you know, for finitely many steps. But you can see that we end up with an object. Doesn't quite look like a snowflake. In fact, it isn't a real shape of a snowflake. We'll see some of those later. But it has this fractal structure, which means that the boundary is very rough. In fact, it turns out that if you try to find the length of the boundary, it becomes infinite. Because there's a corner in the limit, there's a corner at every point, and you have to go around that corner. And this structure is also self-similar. So again, what we did was that we took this triangle, we removed the middle third, took this triangle, we removed the middle third of the three sides, we added a corner, and then we can continue to do that. So on this picture, what we removed is is painted green, and then in the end, we'll end up with a lot of corners. And the structure that you are getting the same thing on a smaller and smaller scale is called a self-similar structure. And now let's see what that means. What that means is that if I look at the bottom corner and I zoom in, so imagine that you have a lens, a zoom lens, and you zoom in and you continue to do that, you see the same structure repeat itself on a smaller and smaller scale. So this is one step, that's the next step. And you can see that you're getting closer and closer, but you're seeing the same thing on a smaller and smaller scale. So fractals are self-similar. They have a very rough structure and they have a scaling. So the self-similarity is manifested in the fact that if you zoom in and you get a smaller and smaller scale, then the same pattern repeats itself. Now, there are many other examples of fractal. The next one I'm going to show you is called the Sierpinski gasket. And see if I can make this a little bigger. You start with a solid triangle, which is this red triangle, but then you remove a triangle in the middle. So you remove this black piece here. And then you keep doing this, you keep on moving, the middle 1/3. It turns out that, what we've done is that we have split the triangle into 4 pieces of equal area, and we removed the middle third. And if we continue to do this, this is the next step, and then we continue, and you can see that we're getting a self-similar pattern, the same pattern on a smaller and smaller scale. And in the limit, it's like these black pieces fill the complete triangle, and you can't even see the red anymore. Now, we could do things differently. We could start with a black triangle and remove the middle third, the middle fourth, excuse me, the middle triangle, so 1/4 of the area. And then you would get a hole there, and then we could continue to do this. And this is where the name gasket comes from. That if you do this, then you get smaller and smaller triangular holes. And this structure is a rough gasket, and it's self-similar. If you hone in, you see the same pattern on a smaller and smaller scale. Now, there are many other examples of fractals, and let me show you another example. This is called these fractals are called the Julia fractals. Actually, I'm going to show you. Let me first show you this example, which is a fern, the leaf of a fern. And what you notice about this leaf is that it has a shape. It kind of is bent, towards the right upper corner. And then it consists of, one stem and then a bunch of leaves attached to the stem. And these leaves, they have the same shape as the overall shape of the leaf, of the big leaf. And they are also attached to the main, stem with their own stem. Now they're either bent towards the right or they're bent left, but the shape is similar. And if you look closer at each leaf, you see that they consist of similar leaves with the same shape and so on. So what you're seeing is that you see this pattern, the shape of a leaf, and then it's repeated on every subleaf on a smaller and smaller scale. So this is a good example of a living object, a leaf of a fern, which is a fractal. It has this rough structure, and it has a shape which is self-similar. It's repeated on a smaller and smaller scale, and you can also see that there are lots of holes, just like in the Sierpinski gasket. Here are some other fractals. This is called a Julia fractal. And you can imagine that if you look at this, that you could imagine that it was a galaxy or, some celestial object. Here's a couple of more Julia fractals. It turns out that they're all controlled by the Mandelbrot fractal, and depending on which point you pick on the Mandelbrot fractal, you get a different Julia fractal, and these are the shapes that they come in. And here is the Mandelbrot fractal itself. Now, I'm not going to go into the theory of the Mandelbrot fractal. Mandelbrot was a French American mathematician who spent most of his life in the States, and he developed the theory of fractals. And a lot of what we know about fractals comes from his work. Now let me stop looking at these examples, and we'll go back to our talk. And here is an overview. I'll give you some examples of fractals from the real world. And then I'm gonna discuss the big fractal that we all live in, namely the surface of the Earth. And that fractal consists of river basins. We all live in a river basin. I happen to live in the Devereux River Basin, and you should figure out for yourself which river basin you belong to. And the shape of the basins is originally and ultimately shaped by the river flow, and we'll explain, how that comes about. So let's start with some examples of from the fractal world. And here is our friend, the fern. It turns out that some of the fractal geometry that you see in the fern can also describe stochastic processes that describe stock market fluctuations. So that's an interesting connection, of the fern and the stock market. The Nautilus shell is a very interesting example of a fractal. What you see here is that there is a shell that can fit into the golden square. So the golden ratio is an important part of it. This is something that people used a lot in Renaissance paintings, and believed that it was more aesthetically pleasing to the eye than other ratios. But the Nautilus shell has this shape, and what you can see is that there are these compartments. They form a spiral, and the spiral can actually be described by the Fibonacci numbers. that some of you may have heard of. And you get these compartments with the same shape, but on a smaller and smaller scale, spiraling towards the middle. In fact, here are some pictures of real nautilus shells, and you can see this compartment. It has a particular shape, and then it's repeated on a smaller and smaller scale, and it spirals, towards the middle. And here's another, similar pattern. Very beautiful patterns that, you see in nature, and that snails utilize, and many sea animals, to build their habitats. Now, here are some examples of snowflakes. Now, a snowflake is formed by super cool liquid or water high up in the atmosphere, which doesn't freeze until it finds a tiny little speck of dust that it can collect on, and then it freezes, and the tiny little irregularities on the surface of the dust are magnified into these beautiful patterns. And you can see, that snowflakes, they come in all different forms. These are some examples. And it turns out that some of these patterns, or some of these processes that can give us the self-similarity of a snowflake, can also describe what happens when people have a heart attack. So there is a connection, and a connection there that you wouldn't suspect. Now, here is a real snowflake, and you can see the pattern that, there was a speck of dust, a tiny speck that you can't even see in the middle, but that gave rise to, this symmetric pattern, but a pattern which is self-similar. So if you hone in, you see it repeat on a smaller and smaller scale. Here is another example, which is quite famous, and that's a coastline. Turns out that coastlines, they are fractals as well. They have a fractal symmetry. Now, they also have inlets, which, are sometimes inlets from rivers. And here you can see, a picture from space of a coastline, and it shows pretty well, the fractal structure. If you zoom in, you see a similar pattern repeated on a smaller and smaller scale. And fjords also have a fractal pattern. This is a particular fjord that I like. If you look, from satellite photographs, this is the western fjords of Iceland, and I like this one. It has a self-similar pattern on mountains and fjords, and this fjord here in the middle is, and at the very bottom of it was the farm where my grandmother grew up. So I like that one. Well, our man-made world does not consist of fractals. We like to build the buildings, and more or less our buildings are made out of little boxes. Sometimes, we get creative and we have various sizes of boxes, but the basic concept is a box. And that's not a fractal. People tried hard in Renaissance time to make sense of the human body, and they tried to fit it into the golden triangle. And here is a famous picture of the Vesperian, where you see a golden triangle and then a circle, and this was supposed to explain the shape of the human body, but it didn't really work. Here, on the other hand, is something that looks more like a fractal, and that's a tree. You know, the bark has a fractal structure. The branches, the trunk and the branches are fractals, and the leaves on the branches are also fractals. You know, here you can see more clearly that there is a fractal structure frequently in the branches. You know, they repeat themselves on a smaller and smaller scale. Sometimes the shape repeats itself as well. If you look at the leaves, you can see the same structure on a smaller and smaller scales, and in a different branch structure as well. And then if you look at some inanimate things in nature, like a lightning, it has a fractal structure. And the way that crystals grow gives them a fractal structure as well. So lightnings have a fractal structure and crystals do. What else? Well, there are many things in the human body that have fractal structures. If you think about our veins, they have a fractal structure. And we have small arteries, and then they split into small. We have big arteries that split into smaller ones, that split into still smaller ones. Our nerves also have a fractal structure. And if you look at our brains, our synapses in our brains, they seem to have a fractal structure as well. The skin has a fractal structure, and people suspect that the way that the cells organize themselves, you know, to form different organs, uses a fractal structure as well. So we may mostly be made out of fractals. But the fractal that we're going to talk about today is the Earth. And it all starts with erosion. So let's imagine that we have a mountain, and then we have a bunch of water, you know, which is this blue ellipsoid on top of the mountain. The mountain is made out of sediment. Sometimes there's a rock, but, you know, let's just say it's all sediment. And then the water runs down the mountain. You know, the mountain gets rained on, the water collects on top and runs down the mountain. And when it does that, it carves out the mountain. And a typical structure that you get is this pattern of river valleys separated by mountain ridges. And the mountains ridges themselves are carved into canyons. And then the canyons have sub-canyons and so on. And if you zoom out, you see the structure. And if you zoom in, you see the structure repeated on a smaller and smaller scale. Here is a typical view of a mountain range. If you look at it from the top, you can see this pattern of rivers and river valleys, you know, separated by mountain ranges, and the shape of the surface seems to have a fractal structure as well. This is very easy to see. Every time you go in a plane, you're looking at these fractals. And in particular, around Santa Barbara, we have a lot of fractal structure in the Santa Ynez Mountains. So you can explore this the next time you fly. And the way these fractals are formed, we can think about it if we make a picture of a mountainside. And let's say that this is a flat mountainside. Maybe it was formed in an earthquake. You could take a very flat lake bed and tilt it, so you get a flat mountainside. then the water begins to run down it. And what happens is that you get these small streams, and then the streams, they unite towards the bottom of the mountain, and they begin to make little rivers, and the rivers begin to carve out the mountains. So first you get several rivers and river valleys, and eventually the rivers themselves unite, and you end up with a couple of valleys, and eventually you only get one big river valley, maybe, branching off into a couple of rivers and then more rivers, and then, two mountain ranges on each side. So we all live in a river basin, and these rivers, they will, carve the whole surface into basins. So there's a separation, from the continental divide of a basin, basically. That separates one basin from another. This is the Katchilaput River Basin in near Fort Collins in Colorado. There's a reason why I like to start with Colorado. But what you notice is that every river basin has a main river, which is this Katchilaput River, which sort of goes along the direction of the basin, and you can see that the basin is a little longer in the direction of the main river than perpendicular to the main river. And then there are side rivers, that come down the valleys, and they unite in the main river, and eventually the main river flows out of the basin, and the rivers on the east side of the Rockies, they will eventually be united in the river basin of the Mississippi. And so will the rivers on the west side of the Appalachian. So there is this huge river basin that collects all of these rivers, and that's the basin of the Mississippi River. That covers most of the continental United States. Now, so we all live in the river basins, and they all have this oblong structure. And one can actually understand from the self-similar structure why the structure is oblong. Here is another basin, and this is the biggest river basin of them all. It's the Amazon River Basin. And you see the same structure, there is a main river, that flows towards the Atlantic. And then there are smaller rivers that join this main river. And here also, the shape is a little longer in the direction of the main river than perpendicular to the main river. So it's a universal scaling. It turns out that river basin have, the sub-basins, they have the same scaling as the big basins. And this gives rise to a famous scaling law, which is called Hack's law for river basins. But where does it all come from? Why are we getting these river basins which have this oblong shape? Well, to understand that, we have to look at river meanderings. And here is the Mississippi River, and you can see that when it's flowing along the flat land, the river likes to meander. When it's going through steep canyons, most of the time it does not meander, it just continues to dig itself down. And in fact, wherever there is uplift, it will dig itself down. The greatest example of that is the Grand Canyon, where you have had significant uplift over millions of years, and the river has dug this beautiful canyon. But if it's going over flat land, some of it has created itself, by carrying silt, towards the ocean and depositing it there. Then it meanders. And we can understand where this tendency to meander comes from. Here is an experimental river. And the way you get it is that you just have a source of water at the top of an inclined plane in the laboratory. So this black square here is where the water comes out from. And if you just let the water flow out from that spigot, and there is no noise, it will go straight down the plane. And this is picture B, and you will just get a straight river coming down the plane. But if there is a tiniest amount of noise, and there always is noise in nature, in fact, in the laboratory, it's enough just to play rock music that will introduce enough noise, the river begins to meander. It begins to meander on its way down, and these meanders, they can be big, but they can also be small. And it meanders all the way down to the bottom of the plane. So this is where the structure is coming from. It turns out that the water flow in rivers is turbulent. And the turbulence involves a lot of instabilities in the water flow, and the tiny noise will initiate these instabilities, and then the instabilities will magnify the noise until you get a fully blown turbulence. And the scaling in this fully blown turbulence is what makes the river meander. Over time, it will meander over this whole surface, and the surface will get the fractal structure of the water flow, and then the river basins will inherit this fractal structure. So it all comes from turbulent water flow, and if we understand the scaling of turbulence, then we can understand the scaling of river basins and of the surface of the earth. Now, we're not the first ones to discover turbulence. In fact, Leonardo da Vinci was fascinated by turbulence, and he did a lot of drawing of turbulence. Here is water flow, probably in the river, I don't know, going around an obstacle and becoming turbulent. And here is his famous drawing of a turbulent pond or turbulent eddies. And what you can see is turbulent structure and on a smaller and smaller scale. And this is where the self-similarity of turbulent flow originates from these small eddies, which are created by magnifying the noise in the water flow. And then that whole structure will be magnified into first river valleys, and then river basins, and eventually the surface of the earth where we live. And that is really the end of my story, and I hope you enjoyed this brief incursion into turbulence. Thank you. Now, in this second part of the lecture, we're going to try to synthesize what we learned in the first part. So if you didn't listen to the first part, please close this part down and listen to the first part first. But what we're gonna do now is to look back at some of the objects that we talked about in the first part. And let me share the screen. And here is the construction that we used in the first part to construct the Koch snowflake. And you remember that we had an equilateral triangle, and we took each part or each side of the triangle. We cut out the middle third, and then we added a corner. Now, this process of cutting out the middle third of a line is the construction that the mathematician Cantor used to make his Cantor set 150 years ago. And the construction that people use to make fractals is really based on his method. You know, he took just a straight line segment, say of length 1, he cut out the middle third, then he cut out the middle third of the remaining 2 segments, and so on. And in the limit, he got the set that is called the Cantor set. Now, what we did was to add a corner, you know, to close the cut that we had made. And we always made these corners be oriented out. You know, and here I'm making it oriented up. But we have a choice, you know, if we now cut out the middle third of, you know, these 4 segments that we made out of the one original line segment, then we could let the corner either be oriented up, you know, up or out or down or in. And we're going to do that just by flipping a coin. If we need to close a cut, like we do here, if we get heads, then the orientation is going to be down. If you get tails, the orientation is going to be up. And similarly here, so we got heads, here we got tails, so the orientation was out. Here we got heads and the orientation was in, and so on. And then we continue to do this. And what we get in the limit is a coastline. So you can see that we can use the same fractal structure, same construction as we used to construct the Koch snowflake to construct a coastline. Now, of course, this coastline is a little artificial, just like the Koch snowflake was an artificial snowflake, and the scaling of a real coastline is a little bit different. But you can understand that it's a fractal because you can think about the surface of the ocean as a plane, and then the coastline is formed where that plane intersects the 3-dimensional fractal, which is the surface of the Earth. And in the first part of the lecture, we saw that the surface of the Earth is a fractal, which is formed by rivers, and the rivers themselves have a fractal structure and the flow in them, and that's because of the turbulence of the water flow in the rivers. Now, the perimeter of the Koch snowflake is infinite, as I mentioned before, and we can easily compute it. And let me go through that computation with you. So I'm going to distinguish the length of a line segment and then the length of them all, or the perimeter. And little l is the length of a line segment, and capital L is the length of the perimeter. Now, when I started with the original triangle and I made the first cut, every line segment was turned into 4 segments, 1/3 the length. So altogether, since we have 3 sides, we're going to get 12 segments. Each one of them has length 1/3. And if we multiply 1/3 by 12, we get 4. Now, in the next step, I'm going to have segments of length 1/9, because every time that we make a cut and at the corner, we shorten the line segments by a factor of 3. So next time, we're going to get 4 squared, because each segment gets turned into 4. So we have 4 squared times 3 divided by 9. And continuing this, it's not difficult to see that in the n step, the perimeter is going to be 4 to the n, or 4 multiplied by itself n times, divided by 3 to the power n minus 1, or 3 multiplied by itself n minus 1 time. And that's because, we're always adding a power of 3 downstairs, but there is 1 3 upstairs that cancels the powers downstairs, and that's why you get n minus 1 downstairs and n upstairs. So we have 3 times 4, we have 4n divided by 3 to the n minus 1. And that's the perimeter after n steps. Now here you have a formula where if you keep on increasing n, the numerator is going to grow faster than the denominator, because 4 is greater than 3. So in the limit, when you take n all the way to infinity, the perimeter becomes infinite. So even though the original perimeter was 3, when you keep on adding corners, and you do that infinitely often, you get a perimeter that's infinite. We can also compute the dimension of the quad snowflake. You basically cover the perimeter with little boxes, and then you count these boxes. I'm not going to go through that computation, but it turns out that the dimension of the quad snowflake is not an integer. It's 1.2618. And this is typical for fractals. Their dimension is not an integer. They lie, most of the time it's an irrational number. Here we get an irrational number, and it lies between 1 and 2. So the dimension is somewhere between 1, which is the dimension of a line, and 2, which is the dimension of a plane. Now, at this point, we might want to ask, look back and ask, what kind of fractals have we gotten? Well, we got a fern, we got snowflakes, we got coastlines, we got cloud formations, we got branches, barks, roots, and leaves of a tree. We got veins, nerves, synapses, and skin of our cells, of human beings. And we got fluctuations of stocks and interest rates. And finally, it turns out that during the Big Bang, there was some small noise, and there were great instabilities, and these instabilities magnified the noise and colored it. And what came out were the galaxies and their distribution in the universe. So the distribution of the galaxies in the universe actually has a fractal structure. So not only are we living on the surface of the Earth, which is a fractal, we're living in a universe that has a fractal structure as well. Now, what is causing all of this? Well, if we go back to our example of the surface of the Earth, then that all started with white noise, which is in fluid or water that's flowing in rivers and over the surface. And because of the instabilities in this fluid flow, this noise gets magnified and it gets colored. It's given characteristics that turn the fluid flow into a turbulent flow. And then this turbulent flow has a scaling, and it gives that scaling, to the surface, to the river basins, and eventually to the mountain ranges and the surface of the Earth. The same thing happens in a seed that will eventually become a tree. You have white noise, and then you have instabilities because that seed is going to grow and become a tree, but the noise gets colored in a different way depending on where it's forming, whether the part of the seed is forming a branch, a root, or a leaf. And the same thing happens in our bodies. There is this white noise, and then the egg grows, and there are great instabilities. It magnifies the white noise and colors it, and the color is different depending on whether the egg is going to form, or the cells are going to form veins, nerves, synapses in the brain, or skin cells. So in general, what is happening is that there is noise, there are instabilities, the noise gets colored, and it forms a fractal. And what I'm going to encourage you to do now is, next time you go outside, is to look around and figure out which things that you see are fractals and which things are not fractals. And what you will discover, I believe, is that many or most things made by nature are fractals, and the things which are made by human beings are not fractals. There are exceptions, of course. If you go to Barcelona, there is this beautiful church by Gaudi, the Sagrada Familia, and that church is a fractal, or as close to a fractal as you can get, because that's what Gaudi was trying to make. So human beings can make fractals, but most of the time they don't. I'm going to end. I mentioned before that each point in the Mandelbrot set corresponds to a Julia set, and I'll end with an animation showing you, how you can get different Julia sets by picking different points in the Mandelbrot set. But I have to correct one thing from the first lecture. The first picture I showed you there of after I showed you the fern was not a Julia set. It was actually part of the Mandelbrot set, but the rest were Julia sets. So let me stop sharing this and show you the animation. So here you can see the Mandelbrot set. And now what I'm going to do is that I'm going to pick a point. And you should see this point as a pink dot. So I'll take my pen and I pick a point in the main body of the Mandelbrot set. And that's what the Julia set you get. I believe you can, if you squint, you can see the pink dot that I made. Okay, now let's clear that one. And I'm going to pick one in the sort of head of the Mandelbrot set. Then you get this. And if I pick one in one of the buds, then you get this. I can also pick one in where the head is attached to the main body. And this is what you get. Or at the rear end of the main body, and you get this. But then I can pick things out a distance away from the main body, and you get something that sort of is beginning to look like a branch or a snowflake. And if I pick one which is, out in the tentacles, you get something which is more and more like a fractal dusts. It turns out that there are 4 types that you can classify, depending on whether they have an insight or not. And you get them all. Oops. By picking different points in the Mandelbrot set. So, thank you.